Welcome. So today we would be doing our examples on autoencoder and continuing down from where we had done. So in the earlier one where we were doing it with the first and the most easiest one, which is called as MNIST. So the whole idea was that can we make neural networks which are fully connected and help autoencoders in order to learn down representations and use that autoencoder learned representations in order to do classification of handwritten digits. And here the problem which comes down is going a bit more than that, because in case of your handwritten digits, you did see that the background was black, and on that the digit part, whatever pixels were where the handwriting was present over there, that was what was available in white. So it was more of like a black versus white pixels which need to be classified, and then the tessellation of these points or the arrangement of these points will help me in order to understand what kind of a digit is written down over there. And this is where you are dealing kind of with a binary data, because the data is either 0 or a value of 255. There is not much of a gray level transition which happens over there. Now, what we want to do more of doing down is that can we have models, and can these autoencoders also learn to identify between grayscale data? And for that, the first one which we will take down is with a modified version of another data set which is called as Fashion MNIST. So here it has images which are of the same size of that of an MNIST. So it's 28 cross 28 pixel images. These are all grayscale, so 0 to 255 full scale values which are available over there, and these are small images of clothing items or apparels. So there are 10 classes of apparels which are present over there, and keeping in sync with the concept of MNIST. So in Fashion MNIST we have 60,000 examples for training and 10,000 examples for testing, and you have 10 different object categories in which you need to classify. So let's get started with what we will do. So since I have already explained about two different kinds of training and autoencoder, so one of them was called as the end-to-end training, in which you create the complete autoencoder. Say I have my input layer, I have the first hidden layer, then the second hidden layer, then on my decoder side I should have one more hidden layer, and then my reconstruction output over there. And then I train this end-to-end in order to do a representation learning, then chop off the decoder part with the hidden layer and the mapping to the output, and then I just have something remaining from my input to the first hidden layer to the second hidden layer. The third is chopped off, or the decoder side first hidden layer is chopped off. Now from here I connect it down to a fully connected network in order to do. So this is the first version, which is called as an end-to-end pre-training of a autoencoder, and then we will use that for MLP initialization in it. So there is also another version which we have on the example, which is called as 13B. So on the 13B example, you would be seeing a layer wise pre-training of an autoencoder. So where that was the other way of doing it, so that I start with one layer at a time, train on the first layer, then train the second layer, then I would be connecting it down to a fully connected layer over there. So let's get done to it. So first part is just my header for fetching down all the libraries over there. So let's run the first part of it. So and this header is more or less constant for all what I am using. So there is not much to actually do around over there. The data set over here is a bit different. So you need, but the good thing is that it's available within the Torch Vision data set itself, and you can directly get it down. So this is called as Fashion MNIST, and now what we do over there is that we just integrated down multiple of these paths over there. So initially this is the part which was to download all the data. That is what I was running down earlier, and then once I have the data downloaded, then I was again using the path over there, and then doing a batch loader with it completely. Now here we have everything taken down together such that in one single shot I have my training data available to me via the train loader pointer. So similarly I can do the same thing to get my testing data as well loaded down via the test loader pointer, and likewise that I have set my download equal to true. So if you are running this for the first time, it will start to download the whole data. This might take a bit of time, but not significant if you have a good amount of bandwidth available over there. So a couple of minutes, and then it downloads and you are good to go. And once it's downloaded, you can just keep on reusing. The only point is that please don't delete the folder from where the data is placed, because every time it's going to look into this one as per this code, or if you copy this somewhere, then create a FMNIST folder or whatever folder where you are just putting on your zip files or tarball images of what got downloaded, then just put down the exact path over there, and that should be solving down your problem. So here we have loaded out the data. The next is to look into the sample. So I did mention that we have 60,000 samples in my training set and 10,000 samples in my testing set, and that's what comes down over there. Now from there, let's get into the next part, which is my sample image from the data set. So let's try to look into one of these images. So this is one image which just comes up for me, looks like a shoe most likely, and then if you see, it's 28 cross 28 and a perfect grayscale image which is coming down to me. Now from there, doing a check on the GPU availability or not, and here is where I start defining my autoencoder. So remember that in our autoencoder there were two parts of it. So one was an encoder, another was a decoder. So here my encoder connects down 784 neurons or 28 cross 28 to 100 neurons. That's the first hidden layer. From 100 neurons over here, after a ReLU or rectified linear unit transformation, it connects down to another 100 neurons, the second hidden layer over there. Now similarly, my decoder side should have 100 neurons connected to 100 neurons, which will map down my like output of the second hidden layer onto something which is conformal and equivocal to my first hidden layer itself. Now once it maps it down, I connect down 100 neurons to 784 neurons, which goes down to produce an output of the same size as that of the input itself. Okay. So this is my initialization and my definition for my autoencoder over there. Now with that, my forward pass, what I need to do is that I would do a forward pass over the encoder, then again a forward pass over the decoder, and just return that result over there. So this is pretty much how my network gets defined. So let's just define the network and get it running. So my network gets defined over there. The next part is that I would start down by training my network. Now remember over here, so we are doing a autoencoder mechanism over there. So what I would technically be doing is that all my outputs are supposed to be the same as my inputs. So while this is the very generalized form of trainer which has been written down over there, the point which we make sure that my labels and my inputs is the same. So label is technically the term which we would quite often be referring to while saying what is the output coming down from a neuron, and because most of the problems are classification problems, so that's the classification label which comes out. But here, since I'm doing a regression learning problem, what I would do is that I can put down my input equal to label while my training, and then my cost functions appropriately get evaluated over there. So going through the rest of it is that you zero down the gradients over there and then map down your outputs and inputs over there, which gets a forward pass through the model, and use a criteria. So the criteria over here, which is defined a bit later on, as we had seen in earlier examples, here we would be using mean square error MSE criteria, because this is just trying to reconstruct itself over there. Okay. Now from there we go on the learning update rules over there. So learning update rule is just going to use down my optimizer and a step function over there, and we are going to make use of the standard stochastic gradient descent as we have been doing with the other ones as well. So now that I keep on doing, so the final part is that I get down my errors and then I can keep on printing them just to see it out. So let's just execute. So this part gets executed for me, and then I have my function for training this network which gets defined. Now once, and remember that this is just for the autoencoder part, we haven't yet come into the multilayer perceptron. So given that, I need to initialize my model and then start the training. So this initialization over here, which I do, is basically take the whole autoencoder model and then see it's randomly initialized. So one part is just print down and check out whether this is exactly what I wanted to see. And so you see that this is the model which I wanted to define, right? 784 neurons going to 100, from 100 to another 100 at the second hidden layer. So on the decoder side, I have a sequential, I have a symmetric way of decoding. So from 100 it goes to 100, and then from there it goes to 784. The weights are again copied down. This is just to check down what is the amount of difference in the weights which comes down before training and after training. Okay. So from there, let's get into the criterion part. So my criteria for costs function is the mean square error MSE, and the optimizer I am using is SGD with learning rate of 0.5 and a momentum of 0.9. So this is quite similar to the ones which we had done in the earlier case with standard MNIST as well. And then I called on my trainer module, and this trainer module function is what was written down over here. Okay. So my reconstruction model, or my just an autoencoder model. So let's run this one, and here it's set down to 2. It takes a bit of time, so I mean I can change and make it pretty much 5. You can run it down for 10s, 50s, 100s, but what we have experienced is more of it goes down to 30, and then whatever it starts reproducing is quite conformal. So going beyond 30 epochs does not bring any major change over that. However, the only major issue is that when we start doing it, it takes about 3 seconds in order to complete each epoch. So that's for the sake of experiments over here within the class, we are just keeping it quite lower to just 5 epochs, so 15 seconds, and this is where you see that it has come down. Now there is a substantial possibility of it to go down even further and keep on decreasing, but I would leave it up to you. So just make it run down beyond just 5 epochs. Going down to 30 epochs, you will get down a much lower error coming down. So this was just the reconstruction error in terms of your mean square error MSE taken down. Now let's look into like how good did the network learn to reconstruct the data itself. So if this is the original image which was given to the network, this is something what the reconstruct is. So the form factor of it remains almost the same, except for that there are a lot of these holes which get created over here, and there is a bit of blurring and smearing which happens to the original form of the shoe which was there in the original image. Now you keep on training it over a longer period of time. You can put down denoising criteria over there, and they can pretty much get rid of these small dots coming down, and so we will be coming to them in a bit later on when we start doing things called as stack denoising autoencoders, and there we will be bringing in the concept in terms of fully connected networks, and then you can just integrate them and keep on running. So here I would just like to look into the weights of the kernel. So we do a copy of the weights after the whole training process, and this is where I just write down a small routine in order to display my initial weights, my train weights, and then what is the difference of the weights. Now if you look into the train weights as well, so they too appear as if not learning down any distinct pattern as such, and quite similar to the noisy nature as in the initial weights. So but whereas if you look into the weight difference over there, you would see that a substantial number of weights have actually been updated. Keep on running it for a longer duration of time, you will definitely see down more updates coming down. Now this is where comes the interesting part, because here we need to get rid of the decoder part over there and have just the representation learning part available to me, and then use this representation learning part as an initialization to my multilayer perceptron. So I need to connect down my final classification layers over there. So here what I do is that we would try to define another small network which consists of 100 neurons to just 10 neurons, and then append this module onto the initial part over there. So what I technically do is that I find down, just list down all the children on this classifier module and n dot sequential. So this number of children which gets listed over there. So if you remember, so let's get back into the original definition over there. So my autoencoder over here was defined something which has 2 modules, the first level of the tree. Within encoder module, I have a sequential module, and within the sequential module, this is how things are arranged. Then within the decoder, I have a similar kind of a module. So on my first level of the tree, if I try to find out my 2 children, then they are encoder and decoder. Now if I remove my decoder module, then I am just left with my encoder module over here, and that's pretty much what has been done over here. So remove that part and then just add down my next module. So from after my encoder, I just have this sequential connection, and instead of using ReLU, which was used just for the purpose of reconstruction, we are going to make use of log softmax for classification purpose. Then it's just a matter of copying down the weights and keeping them so that later on we can as well visualize them, and this is what the network now looks like. So your initial encoder part remains the same, the weights are also preserved over there because I did not play around with the weights or reinitialize them, and then I added down another sequential part which connects down 100 features to so 100 neurons to 10 neurons over there, and then has a log softmax of nonlinearity present. So once done, we define the trainer function over here. So this is quite same except for the fact that my inputs and labels are now different. So I will use down labels which are actual class labels coming down over there. My criterion function will actually be changing over there as well, and I will be using a different learning rate in order to do. So this is just your trainer for the new network which you defined over there. And here when I come down to my actual part of what functions to use and how to start training down, so I'm going to make use of negative log likelihood criteria over there, and that corresponds to the final nonlinear transformation which was log softmax, which is used, which is compliant to the dynamic range and the requirements for negative log likelihood to come into play. And then I set down my stochastic gradient descent, but here my learning rate is pretty different because earlier I was just using 0.5, here I am using a 0.01. That's to keep down with the dynamic range of the errors which I get down. My momentum still remains at the same, and I choose to do it with 10 epochs. I can even reduce this, and then for the sake of time I would just put down 5 epochs over here. So let's run this one, and then yeah. You see pretty much it takes almost the same amount of time, 3 seconds per epoch. So over 5 epochs it should be done within 15 seconds, and you can now look into the accuracy which keeps on coming down over there. So as the error keeps on going down, your accuracy also keeps on increasing, and so this is my training loss curve. So this is no more the mean square error, but this is a negative log likelihood error which comes down, and here is my accuracy. So this accuracy is not in percentage but a absolute scale of 0 to 1. You can pretty much see that it's close to 80% accuracy just by training down in 5 epochs, and that's amazing because the point is that when it was not trained, it started down around with a 50% accuracy, which is just a random chance that anything it just classifies as anything else. And from there, from a 50% accuracy going down to about 80% accuracy is not that bad with just a few minutes. So it's not always that your deep neural networks for solving your problems will actually take a long amount of time. It doesn't, and we are not even using a very powerful GPU as such. It's a very standard desktop grade gaming GPU with just 2 GB of RAM, which is available for us to use. So here we do the performance evaluation for the network. So we evaluate, we write down the function in order to find out what is the total testing error which comes down. So what it's supposed to do over here is that it will get down and load all the images which comes down on your testing data, and from there it will feed forward each of these test images onto your network and eventually calculate whether the accuracy has been, whether it has been correctly predicted or not. Now in the training case, you did see that it was close to 80%, and in test it comes down to almost 82%, 82.4% of accuracy, which given the fact that is not a bad, because none of these testing examples are what the network had earlier seen in any ways. And let's get into what happened down to the weights after all of this training go down. So after my fine tuning, which is when I have this multilayer perceptron coming into it and modifying everything, so my weights are still working out, because this was at the end of the first feature representation learning going down to it, and then at the end of refinement with the classification coming, this is what happened down as a change, and there have been a significant amount of change. You would see that they are getting down more smoother and smoother. Run them down for more number of epochs, not just restrict them to 5 epochs, but say 30 epochs, you would start getting down beautiful emergent patterns coming which can represent this data in a much better way. So here we try to look into the weights of the classifier. So this is what the classifier initial weights which were randomly, so this is the last layer which we added down from 100 to just 10 neurons over there. So this is what it was initially looking like. This is after the training over there, and these are the weights which got updated and the magnitude. So this is one of the versions which works out, and the end-to-end pre-training one. The next one which we do is the 13B. And what this does is that instead of doing an end-to-end, we try to look into layer-wise pre-training, or the second approach of doing it. So going down with the flow over there, so this is my header which just works out fine. Then I have my dataset loader which also works out fine, and so these are all standalone independent codes, and we made it a point that instead of juggling, letting you juggle between copying down which snippet and pasting it over there and then run down the whole scratch, we have written down complete versions of it, and which are provided for your use. You can download each notebook, and each is a self-sufficient exercise with the complete module written down over there, so that you don't face a problem for your initial trials and learning exercises. So we take down, and yeah, it comes down to the same image itself. Because we just did not randomly fetch, we fetched out the first instance of the image from there. Yeah, so run that down, and here we come down to the definition over here. Now for my autoencoder class, in so layer wise pre-training, the whole idea was that you train one layer at a time. Okay, so if I have two hidden layers of 100 neurons, so my first job is that I will train down my first hidden layer of 100 neurons, and then I will go down to my second one. So this is how I define my encoder and decoder. So the first encoder unit takes in 784 neurons, goes to 100, and then from 100 it reconstructs the 784 neurons once again. Okay, now that this is defined, so we will be defining our whole network. So here the input and output is going to be this still the same, and this is what comes down. So if I run and execute my trainer function, then I can actually look into my network, get it transcoded onto a GPU. So this is what it looks like, and copy down the weights in order to visualize it. Now subsequent to that, I have my standard MSE loss function SGD as an optimizer with the same momentum and learning rates as I was doing, and then I just train it for a few epochs. So I change it down and make it 5 epochs, and I just keep on training. So the codes which will be available on GitHub may have some variations from what is present over there in terms of this number of epochs and arguments. They are pretty much commented, and I'm showing it to you as to which points need to be changed over there. So just play around with them. We might put down deliberately 30 epochs over there, so that you run initially for 30 epochs and see. So this is what comes down with just one single hidden neuron. Okay, now here I would like to see just that one single hidden layer, what is the kind of a reconstruction which I get now. Okay, now the next part is, this is when my first bunch of hidden layer connections are already trained. Now the objective is that I would remove my connection from 100 neurons to 784 neurons, and rather replace that one with another 100 over there. So I can look into this as splitting up the decoder, encoder and decoder as in the earlier case. So I have 784 to 100. Now I will bring in a batch of 100 to 100. This gets my second hidden layer. From my second hidden layer to the earlier hidden layer, there will be another neuron connection which has to be established and done. So that's what I am doing pretty much over here. So in my so first what I am doing is, on the encoder module I am adding a module. So this will append itself to the 784 to 100 neurons. So after 100 to another 100. In the decoder side, I need to redefine this one by saying that first I will add 100 to 100, and then the rest of the decoder gets added over here, and that's what I define over here. Now once we do that and look into the network, this is how the network looks like. So I have 784 to 100, 100 to 100 coming down. It looks a bit different because yeah, the number of pointer reassignment just went up, so the hierarchy of the tree is also split up. So that's on the code side of it, but as a function it does not make any change which comes down over there. Okay, now that I have this, so let's run the trainer for this one, and here it was just set down for 2 epochs, so we will just run it for 2 epochs and then look into what comes out. So this is how the actually, so pretty much since the error is going down, you can keep on training it for even longer duration as well. So here let's look into the reconstruction over there. So as I increase the layer, yeah, I mean, to a lot of people you might say that the blur has increased over there. Yes, but then the network hasn't yet learned completely. So you learned on the network over a longer period of time, your errors will keep on decreasing, your reconstruction efficacy does definitely increase significantly. Now the next part is when I need to remove all of these decoders. So I have my 2 hidden layers for representation learning perfectly trained. I need to remove the decoder unit over there from my autoencoder. So what I do is just in the same way, I come down to the first level over there, first level of the tree, and just remove the last terminal element, and then this is what I am left down with. So I remove this part. So I have 784 to 100, then again the next level 100 to 100, and then my output over here, which is my classifier, gets 100 to 10 features, and then a log softmax which is appended to it, and this is pretty much similar to the network which we had in the earlier case. Now doing that, we have a function for training it which is pretty similar to what we had earlier, so I am not discussing much in detail about it, and then we get into the loss function and do it. So we will change this epochs and make it to 5, and let's see what comes out over there. It would take you approximately 3 seconds, as we had in the earlier cases as well. And please don't be much worried about these warnings. I mean, this just with some syntax errors which keep on creeping in with the change in generation of these libraries which come up. So yeah, so it took about roughly 16 seconds in order to train down for 5 epochs, and this is the accuracy which we get, which is again quite closer to 80% as we see. Now we would like to even evaluate this network in terms of its total accuracy, and that comes down to about 72.95%. Now you might have an impression that in the earlier case when I was doing an end-to-end pre-training, it was giving me an 82%, whereas here that I have done layer by layer pre-training, I am not getting that high accuracy. But we need to keep one thing in mind, that in none of the cases the whole network was trained completely, and then if we are able to train it over the whole duration of the epochs, then it's pretty much possible that it would train down in a real good way and give you a much better accuracy, and that's actually the point over there. So with layer wise pre-training, it does take a bit longer to train, but the convergence criteria and the total performance is much better than what you can expect on with the end-to-end pre-training, though theoretically both of them are supposed to converge onto the same point, but then we are speaking in terms of a trainable function and its stochastic behaviors, which are not necessarily always guaranteed to converge onto the same point. So if you look into the weights over there, so between my encoder weights and after this fine tuning, there are again different kinds of changes which happen. And if you look, so since we are not yet learning down very fixed kind of patterns over there, training it over a longer period will definitely give you a much better way of doing. So here interestingly what came out that from your initial weights, and if you look into your trained weights over there hasn't been any change. So that's really something funny. Maybe the autoencoder actually learnt out representation so well that given any kind of a random combination or possibly the random combination of weights which came down over there was something which was actually true to the global minima point, and that's why this happened. But then don't expect that this is the same one which keeps on happening every time over and over again for you. This is fortunately a good case which we just found out for our exercise over here today. So with that we come to an end with autoencoders and two different kinds of autoencoders. In the next class we will be doing out on color images using autoencoders, and subsequently we so instead of classifying, the next class is on classifying patches of color images. The subsequent next lecture will be where we will be doing a pixel to pixel annotation or something called as a semantic segmentation using autoencoders. So there will be like given an image, you go down to any given pixel, take a small neighborhood around the pixel. Using that information over there, you are going to classify each pixel location, and you do a raster scan over the whole image, and you are pretty much at a point when you can segment out the complete image. So with that, stay tuned and enjoy down more of coding and the lectures as we keep on going now. Thanks.